Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Welcome friends. We will continue to discuss the SwayamPrabha course titled Maritime Structures Under Fire, Blast and Explosion. In the last set of lectures, we discussed about the importance of fire and explosion in detail, the various models being used to understand the fire chemistry and the explosion chemistry, how to compute the shock waves and propagation waves, and of course, we also saw in detail how to estimate TNT explosive for any flammable mixture which is combustible in nature. Once we have that in hand, an idea, then I can always compute the peak overpressure, the peak side pressure, and then I can also estimate the damage induced by these shock waves as a qualitative number which is given in a tabular form. So, we will try to find out the scaled distance or the standoff distance first for the face of the building, the side of the building, the top of the building. Then we compute the scaled distance ZE. From the ZE I can always find out the peak overpressure, and then for the peak overpressure and side overpressure I can compute the damage induced by that shock wave at that distance of the target based upon the table which is discussed in the last lecture. So, now we will continue to discuss further on the same line. So, design for blast sequel 3, welcome to lecture 23. So, the reference material given here on the screen and the further two of them listed on the screen are very important references for this set of lectures. I request to have a copy of these books in your library as well as in a personal library, so that they are very useful references, and lot of numerical examples and MATLAB coding are available and shared in all these textbooks. Please use them and also teach them well when you take up such courses for UG, PG levels in India as well as in abroad. So, friends, welcome to lecture 23, design for blast sequel 3. Before we start proceeding further to understand the design for blast, let us try to ask what are the principles we are going to follow in such design. So, let us say in every design process we have two aspects. What generally we call as capacity and the demand, is it not? So, demand comes from the loads. In my case, it is a blast load for the time being, and capacity comes from the geometry and also from the material, and I should also say some additional support or environmental conditions. For example, you can do fire resistant lining, insulation lining, fire protection coating. These are all additional things which are over and above the material and the geometry of the structural system, all adds to the capacity. Okay. So, now when we start discussing about these two aspects, and we understand that when capacity exceeds the demand, it is always safe. When the capacity is equal to the demand, still it is safe. When the capacity is lesser than the demand, obviously it is unsafe and declared not usable under blast loads. So, now when we talk about the capacity estimate, which essentially depends on the material and the geometry, then one important aspect which we must realize in this design is the material properties are associated now at high strain rates. Because blast induces or blast causes relatively high strain in the material or in the member essentially. Okay. So, therefore, blast resistant design should include strain at higher rates. On the other hand, we suggest no increase in the elastic modulus and no increase in the Poisson's ratio. Without this increase, we simply include the strain at higher rates. Okay? Therefore, friends, how this is incorporated in the design? That is the question. How do we do in the design? How do we, let us say, take care of this in design? Okay, that is the interesting question now. So, what we do in the design, in the, let us say, design for blast loads, we try to compute something called dynamic strength increase. We use a factor to increase the strength under the dynamic loads. So, obviously, when we talk about dynamic increase in strength, then this of course also depends on whether the material is capable to accept this increase. Therefore, we divide in two aspects. One is mild steel, the classical structural steel, other is high strength steel. Now, one may ask me a question, what would be the difference of application of these steel in maritime structure construction? Okay. In maritime structures construction, mild steel can be used for secondary elements, of course load bearing, but secondary elements. Primary elements, then connections, pipeline fixtures, bolts, we will use something which is high strength steel, okay, or weldable elements, we use high strength steel. Therefore, friends, the dynamic strength increase factor for these two elements need to be different because of simple reason, the stress strain behavior of these two are different. Okay, the capability, the ductility ratio, the strength ratio of these two are different. Fundamentally, friends, the strength ratio and the ductility ratio here becomes different because of the alloying elements which are added to the steel while they are manufactured. Okay. Now, what are these factors suggested by the code? Let us say for mild steel, the code suggests yield strength increase in bending and shear as 1.25. Okay, yield strength increase factor I should say, okay, 1.25. But when it goes to compression and tension, that is axial loaded members, then we will use 1.2. But when we talk about ultimate strength design, then there is no increase in the factor. Can you ask me why, can you understand why it is so? Because in ultimate strength design, we already have something called load factor and material factor. Is it not? We already have them, which is based upon the acceptable level of characteristic strength of materials. Okay, we already have them. So, we do not have to duplicate it again by additional factor of increasing this for dynamic effects. This is for the mild steel. Now, let us go ahead with the high strength steel. Let us ask about this on yield strength in bending and shear. The increase is just 10%. When we do it in compression and tension, then it is just 5%. When it is in ultimate strength, now you can guess what I am going to write, it is going to be no increase in strength, this is 1.0. Okay. Let us reiterate our understanding. Just look at this table, I have just written the same table again in a different format. Okay. Let us reiterate this understanding, why we have done this. Why your dynamic strength increase is proposed. Why do we do this? Okay. So, friends, this is due to the fact that the factors are applied to material strength, because the strength which will participate in blast loads will be at high strain rates. So, indirectly the high strain rate sector is implemented in the design by increasing the dynamic strength of the material. Okay. So, these values, these modified values in yield strength, axial loading, etc., will help us to enhance the static material strength from static level to dynamic level. One may ask me a question, sir, when we are doing only static analysis, why we talk about dynamic level? You know, interestingly friends, blast load is a dynamic phenomenon, is it not? So, we have to anyway include the dynamic effect, the time effect and the impulse effect on the design. So, we cannot avoid that. Okay. So, when we want to do blast resistant design, then I have to increase the performance of the structural system by adding or enhancing the material strength. We call this as dynamic strength increase factor, which is done on materials. Now, increase the strength, you know, stress strain cover two arms, one is the strain, other is the load or the stress. We have increased the strength part. Now, what do we do with the strain part? Because you know the stress strain curve is proportional. As there is increase in strength, there will be increase in deformation also. Okay. So, let us see what are the deformation limits in the design. Structural elements subjected to blast loading should be designed to respond in elastoplastic region. They cannot be in elastic region, of course, because you know impulse loading will create a permanent dent or deformation on the material and the member. So, the member or the material, structural system or the material will get into or try to enter into the yield Pareto crossing level. So, it will enter and it will cross the yield value for sure, but we should not entertain this to happen beyond the plastic region form. So, elastoplastic region is that segment of the stress strain curve which we are focused in the design. Okay. Now, when we talk about this in two systems, let us say in steel structures and in concrete structures, how do we interpret this? Okay. In steel structures, we interpret this using something called ductility ratio. We check with the ductility ratio and then we implement this so that the design remains in elastoplastic region. Whereas in concrete, you know, concrete is more or less a brittle material, therefore, the ductility ratio may not become a very prominent feature in the design aspect. So, in concrete what we do, we limit it to the joint rotations. Okay. So, there are two different aspects of looking at the design. When you look at steel structural design for blast resistance, we focus on ductility ratios. When we talk about reinforced concrete structures under blast load design, we focus on joint rotations of beam column intersections. Okay. When we say that, then what we do qualitatively, we divide the building into different classifications. We classify building or structures based on two things, based on the structural level or the component level. We can also call the component level as member level. So, two ways I can decide. I will call this as A, this as B. Let us say for the structure level, I divide this building classification into three: low, medium and high. Okay, low, medium and high. For low, how do I assess whether the building is safe under blast loading under deformation conditions? Stress condition we already saw in the previous slide. We are only talking about deformation, that is a response in terms of deflections, joint connections and rotations, only the deformation part. If I want to classify the building as low response, the structure wise, then I should say the localized component is only damage. Building or the structure is repairable because the damage is moderate. Okay. If you see a damage is repairable under the blast loads, I classify that building as low response limit to blast loads. On the other hand, if I have a widespread component damage, there are many components and members damage, let us say widespread component damage, and the building cannot be repaired or cannot be occupied until repair. So, it lost its serviceability, let us say. Okay. When you see that kind of damage or deformations in the structural system as a whole building, then we classify them as medium. In case of high, key components or key members of the structure are damaged and building lost its serviceability completely. I mean, it is beyond repair. You cannot repair the building and occupy. No, it is not possible. So, when you foresee that kind of damage, when you really picturize this kind of damage on the whole structure, we put them on high. Friends, it is very necessary that all maritime structures, even after blast loads occurrence, should fall at least within this range. Okay. We cannot permit this kind of damage in maritime structures. This is for the structural level. Let us move on to the component level. I can say member level. Again in member level, we divide them as low, medium and high. Let us see what do we understand this by low. So, in low level classification of members, you can say damage is not visible at all. Okay. So, we classify them as low level damage. Then in member level in medium, components have permanent deflection. So, there is a plastic deflection induced, but repairable. we call this as medium level. In high level category, the components or the members have faced significant damage and cannot be repaired. We put that category of the structure because of member level observation as high damaged structures. So, the deformation levels permitted for the design of blast resistance are categorically done in two manners, which can be assessed as a qualitative observation. There are no values given that the deflection should not be more than L by 375. There are no numbers like this proposed. Okay? It is a qualitative assessment. Why? Because essentially structures under this kind of high strain rate effects are usually performance based indicators. Performance based indicators will generally be only qualitative. It cannot be quantitative in terms of numbers of deflection, strength value of certain megapascal, you cannot do, because the qualitative indicators will closely relate one-to-one mapping with performance based indicators. Strength based indicators will not have a direct relationship with performance. Performance itself is a qualitative term, right? How do you perform? I perform better. So, there is a comparison, there is a relativity, you cannot make it in absolute terms. So, there are no numbers here, right? That is very important to understand this. Okay. Now, when I say this, the average dynamic strength factors in flexure and compression and diagonal tension in concrete and masonry are given by these numbers. For reinforcing steel are given by these numbers. So, earlier we saw in a different format, now we saw more in detail in masonry and concrete and reinforcing steel, rebars in a different frame, in different mode of failure. Yield strength in compression, diagonal tension, ultimate strength in flexure, ultimate strength in compression. The moment I move to compression, diagonal tension, shear and bond ultimate, there is no increase allowed, but you can allow this only in flexure, because again there is a factor of safety or margin safety operated in reinforcing steel in ultimate strength in flexure, but it does not happen in compression and diagonal tension because they can cause instability. Okay? This is because it can cause instability. Therefore, we do not recommend increased numbers of dynamic increase factors for design of blast resistance when we talk about these applications, but rest are all okay for reinforcing bars. So, the deformation limits we reiterate, that is what we just discussed about in building level and in component level damages, right. So, when we also look at the blast resistance of flexural members in terms of maximum permissible deflection, we also then check at the rotation capacity and ductility for reinforced concrete members. Okay. If you talk about the flexural member, look for maximum permissible deflection. If you look for concrete structures blast resistance, look for support rotation and ductility. Support rotation for concrete and ductility ratio for steel members. The maximum permissible deflection limit defines the energy absorbing capacity of any element. So, the level of deformation parameters given for steel and concrete. Let us say for example, ductility ratio in structural steel, if you are looking at design target of low damage, then we require a ductility ratio of 3. If you have a medium damage kind of structure, the ductility ratio should be 10, high damage 20 and so on. Okay. If you look on the other hand, the reinforced concrete structure support rotation, then for low damage, medium and high damage, these are the numbers recommended for bending and direct stresses in both the cases. Okay. So, these limits are important. These limits are important because they will help engineers to decide whether a structural member is acceptable or remains functional under blast loads. So, it is sort of a check actually, okay, sort of a check. So, if you apply this check to maritime structures or maritime structures, then the basic requirement is, the desirable requirement is, the structure should be designed with low damage, but it can be acceptable till medium damage, but cannot be accepted with high damage, because maritime structures are strategic structures. Okay. Then we will move on to the next case where we talk about the method of analysis for blast. Okay. There are three methods by which I can analyze the system, structural system under blast loads. One, I can look for something called equivalent single degree of freedom system analysis. You know, structures under blast loads are generally done using dynamic analysis methods, because blast load itself is an impulse function. So, you need to do a dynamic analysis. So, there are three methods of analysis which we propose in Indian Standard Course of Practice for blast design. One is equivalent single degree freedom system analysis. The second one is dynamic analysis detailed dynamic analysis using finite element method. The third one could be experimental and empirical approach of analysis. Okay, the three methods suggested in the code. Let us see one by one quickly. Okay. Let us talk about the first one, which is equivalent SDOF analysis. So, in this, first we need to compute something called effective mass and stiffness, because you are converting the system into equivalent SDOF. So, effective mass participation should be added. In this case, the structure's mass and stiffness, the structural total mass and stiffness are condensed to be a single degree of freedom system spring mass model. Okay, no dashpot, no damping, spring mass model. Okay. Then what is the equivalency? The equivalency is the deflection of the equivalent single degree freedom system should match the deflection of critical points in the actual structure. Okay, that is the equivalency we match. This we have got to match. To do this analysis, we need to compute something called load mass factor. So, we know the mass factor, we also know the load factor. So, now we can find the load mass factor, which is called as KLM, is the ratio of the mass factor to the load factor. It is going to be simply a number, okay, it is a factor. So, this will take care of the total mass and the total load of the equivalent single degree freedom system. Okay. Then once I do a dynamic analysis, I have the mass and stiffness, I need to go for the time period. That is the next obligation I have, time period calculation. The time period calculation is done based on the total mass and effective stiffness. Okay. Then the last one is of course the load deflection behavior, because we are looking for the equivalency of single degree with actual system. So, I have to equate, look at this knowledge, I have to equate the deflection of the equivalent single degree with that of the vital points in the actual structure. So, deflection should match. There is a very important criteria here. Load deflection behavior should be like that. The actual non-linear load deflection is idealized into either a bilinear curve or a trilinear curve. So, while doing this, what do we preserve? You preserve the area under the curve. Up to maximum deflection or maximum permissible deflection to maintain the energy balance. Okay. Let us say how do we do this? It is very simple. I will show you this illustratively. Not very difficult to understand. Let us say I draw this curve as a stress strain curve. The actual non-linear stress strain curve goes like this, let us say. The actual curve goes like this. So, this is the actual non-linear stress strain curve. You can see it is a typical stress strain curve for concrete, right. So, I idealize this in a different form. What do you do? I take a value here and idealize this with an initial tangent, and I call this as idealized elastoplastic curve. Okay. This line is elastic, we all know that. This is the elastic region, is it not? So, it is a bilinear curve now. I should say bilinear approximation. What are the salient points in this? We call this particular point as Rm, therefore, this is called resistance. Of course, this is called, I will replace the name as deflection. You know, I am going to do the equivalency only in terms of deflection. Therefore, strain of course is a parameter on deflection. So, I have replaced the arms of this stress strain curve into resistance and deflection. So, I will call the slope of this initial line as elastic stiffness. I will call the corresponding deflection as yield deflection. Then I will call the corresponding maximum tip of deflection to maximum deflection, Ym. Okay, let me write it here. I will cut this and write it here, Ym, maximum deflection. So, these are the equivalent points which we must consider when we talk about bilinear approximation. Similarly, I can also talk about a trilinear approximation. So, again I draw another set of curves where as usual I will mark this as deflection, not as strain. I will mark this as resistance, not as stress. We already saw the bilinear curve. Let me mark the bilinear curve here first. Let me mark the bilinear curve here, which is identically what I have marked in the left hand. This is figure 1. So, the bilinear curve I have marked is same as what you see in the figure 1. This is figure 2. So, this is going to be a trilinear curve. See how? So, what I do now, I idealize this elastoplastic into 3 parts: the initial tangent, the modified tangent, and then the curve. Okay. So, there are 2 slopes here. I call this as K2 and I call this as K1. K1. Whereas we know the slope of this is already known to me as K elastic, right? We already have this here. So, now what are the salient points here? The first salient point I indicate here is this, which is called as resistance elastic. The second salient point is of course this we call resistance maximum, which is same as this, note that, same as this, because this curve is same as this curve, okay, there is no change. Now, the corresponding strains or deformations called as Y elastic, then I should say this already we know it is Y yield, we cannot change this. Then we know this point as Y plastic, okay, we limit it here. So, now I can say this is my trilinear approximated curve, this is my bilinear curve. So, these are idealized resistance deflection diagram, which we follow in blast resistor design. Okay. So, the first method of analysis is talking about equivalent single degree, which we discussed. Okay. Now, let us talk about briefly the second method. The second method of analysis under blast loads is dynamic analysis using finite element method. So, this is generally applied for more complex structures. So, we can give an example. I can say the structure undergoes large displacements, not deformation, large displacement, rigid body motion, floating structures, form dominant systems, okay, which are all very common in maritime structures. So, they are very complex. For these kind of complex systems, we use detailed finite element analysis. So, what do we do here? We first create something called detailed modeling. in which we include material properties, the full detailed geometry, and of course, all possible boundary conditions. Then, since blast load is an impact analysis, we do time dependent or time response analysis, not frequency response, okay, time dependent analysis. So, we apply blast loads as time dependent functions. We already seen that in the previous lectures, is it not? The peak overpressure, side overpressure in terms of time, time arrival, time delay, we have already seen them. So, we can always express blast loads as time dependent functions, and we focus on the transient response analysis. Okay. So, one may always think about that in dynamic analysis, steady state is very important. So, unless the structure reaches the steady state of vibration, let us not bother about the structure. No, no, it is not true. There are examples where transient response govern the design. I can give some examples. One, the blast load design or blast load behavior is governed by transient response. Second one is the springing and ringing response of TLPs. You can read more literature on springing and ringing of a TLP, right. So, ringing response is actually a typical kind of response which repeats after a long time the same interval. So, this repeats by itself for n number of cycles. This is a very dangerous response system. It looks very transient and it feels there is a steady state setting happening, but again it invoke. So, it is a very, when in schools you must have heard, when the bell starts ringing, then the amplitude gradually picks up, and after the bell stops ringing, the gradually amplitude decreases. But if this is a repetitive cycle, then that is the danger we call as ringing response, and so on. So, transient responses in dynamic analysis are not always oversighted. There are certain segments of analysis applied to structures where transient response becomes the focus. In the present context, blast load behavior is a transient response focus idea. So, we must focus on this. The third one which we must consider in the dynamic analysis is that the material response behavior. The material behavior should include the stress strain effects, which we already saw, bilinear, trilinear aspects, and it should help simulate the non-linear property of material to capture the response under blast loads. Okay. Of course, empirical methods and experimental methods are based upon validating them with large number of set of data sets, which actually result in forming empirical equations and expressions to find out the structural response under blast loads. Okay, that is the third case. The third case is experimental and empirical methods. So, they will lead to equations which are parametric driven. Therefore, they cannot be generally applicable to all structures, not generally applicable to all structures, So, they are actually case specific or system specific solutions. So, they are not therefore acceptable in a generic formats. Then ask a question, why we should do blast load analysis? How to do we have seen, okay? Why we should do, we should perform analysis under blast loads. Why? What is the importance of this analysis? The importance of the analysis are crucial in three parameters. One, safety. It ensures that the structure can withstand the anticipated blast load without complete failure. Safety. Second, cost effectiveness. This helps avoiding over design. Third one, of course, the design should be code compliant. Should follow some codal guidelines. So, as far as Indian Standard Codes of Practice of Design is concerned for blast loads, we have 4991 under revision, structures, design of structures and the blast loads. So, the code revision helps us to understand these details, and the lectures what we are now presenting is an extract of the draft form of these. So, we sincerely thank the Bureau of Indian Standards for giving a very interesting and very detailed oversight of this theory in literature and helping academicians and industrial practitioners to learn the new concept of blast resistant design. Thank you Bureau of Indian Standards for a very wonderful collaborate of research ideas into very nice text forms, which is going to appear in the draft code of 4991 very soon. So, friends, we can also help you in giving some, let us say, shortcut understanding of to compute the time period. For dynamic analysis, if you want to compute the time period, I will always use this equation under blast loads, where it is KLM M total by K equivalent, where KLM is called as, okay, let me use this as small ke. KLM capital is called the load mass factor. We already discussed that in the previous slides, please look at. MT is the total mass of the structure and K small e is the effective stiffness of the equivalent system. For every equivalent system, you can always find the effective stiffness contributing. So, let us recollect to assemble or arrive at equivalent system. What we should focus? We should focus that the deflection of the proposed equivalent system should be same as those deflections at critical points or sections in the real system. Okay. So, deflection equivalency is to be maintained. Okay. So, friends, let us make a summary of this lecture. In this lecture, we learnt the details about blast resistant design. We asked certain questions, how we incorporate the dynamic strength amplifications in concrete design and in steel design, then how we qualitatively check the acceptable level of buildings under blast loads. We categorically divide the buildings into member level and component level and whole structure level as low, medium and high, and we categorically say my structural design falls in which category of this as a building, as a member. Okay? And we also see the dynamic strength factors are very specific to kinds of loading, like for example yield in flexure and bending, similarly tension and compression and ultimate strength. I mean there are different, so very detailed insight has been discussed in this. So please have a look at these lectures sequels again, and we take you forward to one more lecture on blast test and design before we understand comprehensively the whole exercise applied to maritime structures. Thank you very much. Namaste.